Learning target number 2. So learning target number 2 is about friction, and it's defining static and kinetic friction. Okay, so in the slides we talked about what is friction, and it turns out on the microscopic level that surfaces are not smooth. Even surfaces that we perceive as smooth, like glass, actually have all these tiny little hills and ridges, and those hills and valleys, they can become interlocked as they glide past one another, and that's what friction is. Okay. Now there's two kinds of friction that we're going to be talking about. We're going to talk about static friction and kinetic friction. Static friction is when the friction that's preventing something from moving. Okay, so if I have my calculator, okay, and I push on the calculator, but it's not moving, that's because of static friction. I'm pushing it, but it's not moving. Okay. Now, kinetic friction is different. Kinetic friction is that friction that occurs when an object is moving. So if I start pushing it, if I finally push it hard enough, then I'm going to get movement. And now that's kinetic friction because there's motion involved. Now, depending on the surfaces that you're working with, the coefficient of friction is going to change depending on the surface. So different materials exhibit different frictions, and we define that with our coefficient here. So the normal force also plays a role. If we look at our graph here, we can see normal force and then kinetic frictional force. So if we increase our normal force for each type of material, the kinetic frictional force also increased. So when we increase our normal force, we also increase the kinetic frictional force. So those would be proportional. When one got bigger, the other one got bigger. And here's the equations here. So friction static is coefficient of static friction multiplied by the normal force. And then friction kinetic is coefficient of kinetic friction multiplied by the normal force. Now I want you to make one small change in your notes. Okay. Now here's what I mean. The static friction is going to either be less than or equal to its maximum capability there. Okay. So let's pull out the calculator again and show you what I mean. If I very lightly push the calculator, friction is lightly holding it in place. Okay, the acceleration is 0 because the velocity is constant. It's constantly 0. Okay, now if I apply more force, now that static friction is greater because it's still holding the calculator in place. It's canceling out the force of the push here. Okay, and so it starts off, that friction started off really light, and then I push harder and harder and harder, and that friction becomes greater. Eventually, I'm going to push so hard that I overcome static friction and it changes to kinetic friction. Now here's how that would look graphically. Okay. So this is static friction, okay? And as I increase my applied force, okay, so I'm increasing this applied force, then the force due to friction also increases. Okay, so I start off pushing lightly, and then I get pushed more and more and more, and friction gets greater and greater and greater, and then I reach this threshold of motion, okay? Threshold of motion. And that means that I'm finally going to overcome static friction. And so we see something really interesting that happens right here. When I finally push hard enough that I overcome static friction, it's then going to become kinetic friction. And kinetic friction is always less than our maximum of static friction. Okay. Now this should make sense Because think about if you have like an appliance you're trying to move. It takes a lot of effort to get it going, to start that motion, but then once it starts moving, it's a lot easier to move. You can also see this with like a truck, like you have it in neutral. It takes a lot to get that truck moving, but then once it starts moving, then it's a lot smoother, a lot easier. Right? So the maximum static friction is always greater than the kinetic friction. Now let's draw a couple free body diagrams for what's happening here. So down here, we're going to do the calculator. We have a force due to gravity, and then we have the force normal pushing back up. It's not sinking into the table or rising out of the table, so they're equal to each other. I'm also applying a force. It's a relatively small applied force. Okay? But then friction is opposing that. And in the x direction, the calculator isn't accelerating to the left or to the right, and so that friction must be equal and in the opposite direction. Okay? Force due to friction. Now, up here, the force due to gravity and the normal force are the same. It's still the same object. But my applied force is a lot greater. Okay? But the object is still not moving. And so that must mean that the acceleration is 0. And so then my force of friction must be greater as well. Okay? Now, eventually, we're going to overcome that threshold of motion where our applied force is then greater than the friction, and so that motion will start. Now, after the motion has started, and let's say we're now moving, okay, so the calculator is now being pushed across the table, but at a constant velocity. So what would that free body diagram look like then? Well, we'd still have our force due to gravity, and we would still have the normal force. But we're talking about a constant velocity in the x direction. So if velocity isn't changing, that means acceleration is 0. Okay? So acceleration would be 0, which means the sum of the forces would also be 0. And so all my forces better equal each other. So my force applied, has to equal that force of kinetic friction. And I'm moving with a constant velocity across the table. Okay, this is just kind of what we were talking about before, what we were just going over. Okay, we have two situations. We kind of talked about those two situations. Balanced frictional force and an unbalanced frictional force. Balanced just means the sum of the forces are equal to 0. Okay, and that would mean that the acceleration is 0 then. And then unbalanced forces was when the sum of the forces does not equal 0, which means acceleration does not equal 0. Okay, let's see where we're at on time. Okay. All right, now we're going to go over some practice problems. Let's look at example number 1. You push a 25-kilogram wooden box across a wooden floor at a constant speed of 1 meter per second. How much force do you exert on the box? The coefficient of static friction is 0.5, and the coefficient of kinetic is 0.2. Okay, now we are pushing this wooden block across the floor at a constant speed, so that jumps out to me. Constant speed. That means our acceleration is 0, so the sum of the forces are going to also equal 0. Okay. Now, we have a wooden block being pushed across the floor. So if I were to draw a free body diagram of this, I'd say I have a force due to gravity. I have a normal force because that box is not accelerating in the y direction, right? It's not sinking into the table and it's not lifting off of the table. It's constant. Its velocity is constant in the y direction. And then in the x direction, it's also constant as well. But we have some forces here. We are pushing the box. So we have some force applied. And then we know we have friction. And again, if the sum of the forces are 0, then that frictional force must be equal and in the opposite direction of the applied force. Okay? How much force are you exerting on the box? So we want to know what the force applied is. Okay. So because we're dealing with friction, reminder, and we're moving at constant speed, so it'd be kinetic. So the equation for friction, kinetic, is mu k, or the coefficient of friction k, multiplied by the force normal. So we need to know the normal force before we can figure out this frictional force. So let's start there. Let's look at the sum of the forces specifically in the y direction, not in the x for the moment being. Now, again, like I said, the box isn't lifting off the table or sinking into the ground, so I'd say the sum of the forces in the y direction is 0. Now let's list those forces. We have a positive force normal, and we're going to add that, because this is sum, we're going to add that to the negative force due to gravity, or minus force due to gravity. Okay? And all that equals 0. I'm going to take this force due to gravity, I'm going to add it to the other side. So force normal is going to equal the force due to gravity. Okay? Now remember, force due to gravity, that is the mass of the object multiplied by the acceleration due to gravity. Okay? So force normal is the mass of the object, 25 kilograms, multiplied by the acceleration due to gravity, which is 9.81 meters per second squared. Okay? So I'll run those numbers. 25 times by 9.81. 3 sig figs, 3 sig figs, so my normal force would be 245 newtons. Okay? Now, 245 newtons, that's the normal force. That doesn't tell us what we are looking for yet. Let's now look in the x direction, because that's where our unknown is. So sum of the forces in the x direction. Okay. So sum of the forces in the x. Well, it's moving at a constant speed in the x direction, so that must mean acceleration is 0. So sum of the forces are equal to 0. Okay. What are the sum of my forces in the x direction? Well, in the x direction, I have a positive force applied, and I'm going to add that to a negative force of friction, or minus the force of friction, and that's going to equal 0. Okay. So I'm going to take this, I'm going to get what I'm looking for by itself, I'm going to add it to the other side. So my force applied is going to equal my friction force. Okay. And we know that friction is our coefficient of friction, kinetic, because we're moving at a constant speed, multiplied by the force normal. Our coefficient of kinetic friction is 0.2, and then our normal force is 245 newtons. So when I multiply those together, I get 49 newtons. Okay, we just solved for that applied force. With how much force do you exert on the box? Okay guys, so when you come back for the next video, we'll look at example number 2.